Hey guys, this is Darsh Patel from Lab Section MO3. For my Lab 5, Motion of Falling Objects, I observed a tennis ball as my fast falling object and a balloon as my slow falling object. And the main objective of this lab was to analyze the motion of the fall using tracker, and the observed data was compared to a VPython model, in which the first model only had the gravity force acting on the object, and the second model had a gravity force along with a drag force that opposed the motion of the object falling. And the main result I found was that when an object is dropped, it follows a projectile path until it hits the ground. Using the momentum principle we learned in class, it is possible to calculate the velocity in the y direction. As we all know, the velocity in the x direction is constant throughout the fall. You can also use the VPython model to predict the object's location as time goes.
Right here are the videos of the two objects that I observed, the tennis ball on the left and the balloon on the right. And by watching each video, it is clearly evident that the tennis ball falls faster than the balloon. For the coordinate axes, I did not change the orientation, as the negative y-axis was along this line and the positive x-axis was along this line right here. For the time of the video, I started observing the objects from the time they were thrown initially until the objects hit the ground in each case. And the average location of each object was the center of the object. So the balloon was right here and the tennis ball was right here. The initial location of both objects was at the origin. And for my length scale of the video, I measured the diameter of the balloon, and I found it to be 15 centimeters. And for the tennis ball, the length of the diameter was found on the internet, and it was 6.7 centimeters. Here's the model for my tennis ball. I found the mass of the tennis ball to be 57 grams, and I plugged it in right here. Since the ball was at the origin initially, the position vector is 0, 0, 0, and there was no initial velocity, which also means that the velocity vector is also 0, 0, 0 initially. As for my delta t, I decided to use 0.033 seconds. And in this model, the only force that is acting on the object is the gravitational force, which is defined as the mass of the ball times gravity, and it is always pointing in the negative y direction. We then used the momentum principle to predict the velocity as a function of time, and each time the new velocity was found, the position update was carried out. And this is what I get when I run my model. The arrow represents the gravitational force, and it's in the negative y direction, and for the motion of the object, it follows a projectile path until it hits the ground. On simulation of my balloon, the mass of the balloon is 1 gram, and the initial position and the velocity vectors are both 0, 0, 0. The delta t is 0.033 seconds, matching the frame length of the tracker software. For this simulation, the only force that is acting on the balloon is the gravitational force, and the net force is just the gravitational force, as represented right here. The momentum principle was used to predict the velocity with time, and the position update was carried out each time a new velocity was found. This right here is my model, and as you guys can see, the gravitational force is always pointing down, and just like the tennis ball, the balloon follows a projectile path. The tracker data and the model data were graphed on the same graph. As for the tennis ball, the observed data, which is the green triangles right here, and the model data, which is the purple X's right here, are very similar. For the balloon, however, there's a huge disparity. The observed data is the blue diamonds right here, and the model data is the red squares right here. And there's a huge disparity, as the simulation almost traveled twice the distance of the observed balloon video. And this can certainly be attributed to the drag force, which will be explored in the next simulation. In the simulation, the force known as Wish's drag was acting on the tennis ball along with the gravitational force. Wish's drag is defined as negative b times the velocity, and b is a constant which is dependent on the type of the fluid the object is in, and in this case, the air. B was determined experimentally in both of these experiments by picking values and running a simulation to see if the final position of the ball predicted by the model matched the final position of the ball obtained using the tracker software. Here's the model when I run it. As for the simulation run with the balloon, the drag force is still negative b times velocity, and the net force is once again the gravitational force plus the drag force. And when I run the model, the drag force on the balloon is much greater than the drag force acting on the tennis ball, and it is evident by the green arrow that you guys can see right here. As for some observations I made after graphing the data in Excel, the modeled balloon data with the drag force is represented by the blue crosses, and the observed balloon data is represented by the blue diamonds. And as you guys can see, the model does a great job of predicting the motion of the balloon once drag force is incorporated. And for the tennis ball, the green triangles represent the data obtained from the tracker software, and the orange circles represent the model data using drag. And as you guys can see, there are no orange circles even present on the graph, which means that they are completely covered up by the green triangles from the observed data. For what this means, an object reaches terminal velocity when the magnitude of the drag force is equal to the magnitude of the gravitational force. Therefore, the net force on the object would be 0. After the object reaches terminal velocity, there would be 0 acceleration, and the object would fall at that constant velocity throughout the fall. To predict the terminal velocity of a slow-falling object, the model with the drag force is the best one to use. When I run the model, this is the graph I get, and after a certain time period, the velocity reaches a constant number, as it is evidenced by this straight line right here. Here's my computational model of the slow-falling object with just gravity acting on it. I gave the object initial velocity of 1 in the negative y direction, and this is the model when I run it. There is no clear indication of terminal velocity reached, and when I look at the data output, you can see there is no clear terminal velocity. On the other hand, in the model with the drag force, the initial velocity is still 1 in the negative y direction. However, when I run this model, there is a clear indication of terminal velocity reached, and you guys can see that by the straight line right here, and it is also clearly evident in the data output. The object reaches a terminal velocity of negative 2.01 meters per second.